All right, let's talk about the Doppler effect. And we've talked about this many times, but let's kind of get into it in more detail here. So here we've got this bug. His legs are jiggling up and down, and he's standing still. And notice how all of the rings around him are perfect circles. It's nice and beautiful. But what happens if he starts swimming across the water? Then, as he's moving, notice how the crests in the front are closer together than the ones in the back. Okay, so if I'm at B, these crests are coming to me in very short amounts of time, and I see a higher frequency. On the other hand, if I'm at A, these crests are meeting me at longer intervals of time, and I have a lower frequency. That is known as the Doppler effect. That's what they're talking about when they're talking about the Doppler effect. Okay. So the Doppler effect has to do when the speed of sound, or when the object producing the wave is moving, and the greater the speed of that object, the more the Doppler effect will be affected. So here's our fire truck, and we've all seen this, where it's coming at you, and you hear this whee as it goes by. Okay, that's the Doppler effect. And, sometimes the Doppler effect is not good for you. Police cars use the Doppler effect to figure out how fast you're going, because if you're going fast, then those waves coming back to the police car are going to be shorter, and they can detect how long that is and figure out how fast you're going from that. So here's the police car parked. He's going to send out a wave. It's going to hit your car, and it's going to bounce back at a faster rate than what it left his gun, and he's going to measure that rate and figure out how fast you're going. Bats use this to find moths and so on. So, pretty common thing. Light also is affected by the Doppler effect. We've talked about this in the book, Briefer History of Times. Talked about that. As light is moving towards you, light is shifted to the blue side, so it tends to be more blue, anything that's moving towards you. On the other hand, if it's moving away from you, everything is red shifted, and we notice that all the galaxies around us are actually moving away from us. So they're all trying to get away. Sad. All right, when a source moves towards you, do you measure an increase or decrease in wave speed? Neither. It's the frequency of a wave that undergoes a change, not the speed. Trick question. All right, let's talk about bow waves. And this is when we're kind of close to the idea of the Doppler effect, but now we've got the object moving faster. So let's take a look at our bug. He's swimming as fast as the waves are moving away from him. And notice that when he does that, all of these waves pile up right here. Okay, so they're all piled up on this area in this leading edge. And we've kind of got this pile up of waves right in here as he's going. An aircraft does the same thing. As it goes faster and faster, it gets close to the speed of sound, all these sound waves kind of pile up, and eventually it's going to go faster than the speed of sound, and then you get that sonic boom. So when a plane goes supersonic, it's going to have that sonic boom. But the nice thing for the plane is it no longer has to worry about the air. It's really nice. Right before they hit, when they were first trying to break the sound barrier, they had some problems, because as they were getting very, very close to being supersonic, all those sound waves built up, and it was really hard on the plane. And the plane would sometimes, would fail, be shaken apart because of that. But once they pass the speed of sound, then it's fine. Okay. All right, so let's say now that this bug starts swimming even faster. So now, let's go back here. Why are we doing this? So now, we've created this wave behind him. Notice how I get this wave kind of here. All these things kind of pile up, and you get this. And think of the best example is think of a boat. And when you're in a boat and you're moving, behind the bow are these waves right here. And if you go water skiing, that's what you kind of hop over those waves when you're going from side to side. Well, that's because the boat is traveling faster than the waves are traveling. And so they all pile up right here. And the faster the boat goes, the bigger this bow wave becomes. Okay. So taking a look at this example, you got first one, he's going slower than the waves are. And here he's going just as fast as waves, so we have all of these right here. He's got to swim through all that. That's kind of hard on him. And now it's going faster than the waves, and now it's easier for him. And if he goes even faster, they get, you know, the things get longer. Okay. All right, shock waves, and shock waves are very similar to what we were just talking about, except usually when we talk about shock waves, we're talking about them in the air, and we're talking about three-dimensional versus a water wave or a bow wave would be considered two-dimensional. The shock wave is three-dimensional. It's a cone. So we have this airplane that's going supersonic speeds, and it's got this three-dimensional shock wave following it that looks like a cone. And if you are in that area, if you meet that cone, you'll hear that sonic boom as it goes by. And that's going to just sound like a big crack, you know, a big thunderbolt or whatever as it goes by. And all that sound has been compressed there in that area. It talks about here, I thought this was interesting, it talks about the speedboat. If you're standing by the water's edge, you're hit by that water, you could consider that to be a water boom. And here we call it a sonic boom. And we don't hear sonic boom if the aircraft is going below the speed of sound, but only when it's going faster than, and all that high pressure builds up, and our ears can't distinguish that from any other sound, so it just becomes kind of a boom when we hear it. One thing that usually people don't understand is that they think that sonic boom only happens when the airplane breaks the sound barrier, but that's not really true. You're always going to hear that sonic boom behind the airplane as long as it's moving. As long as you meet that cone, you'll hear it at any time. So here's our example. You know, the guy in the red in A, he met the sonic boom. He's already heard it. This guy's hearing it right now, and this guy hasn't heard it yet, but he soon will as this plane continues on. Some other examples of things when you have supersonic, a bullet is supersonic, and so that's why you hear that crack of the bullet. Or a whip, like, you know, when they have lion tamer, that would be an example of something that is supersonic. Or even a towel. If you have a towel and you whip that towel and you're really good at it and you can go really, really fast, that actually will be faster than the speed of sound, and you break the sound barrier, and that's why you can hear that. So